one, study goal number 22. Whatever you answered, I'm sure is fine, but I'd like to add to that. Listen to this list. 22 goes with study goals 3, 10, 23, 25, 26, 45, 48, 53, 54, and 55. There's a whole bunch of study goals about dams. And I want to try to get as much of that out today as possible. So over many, many years, I've noticed that I used to do all those study goals. And then at the end, I would do a separate follow-up where I would just list all this verbally, and kids would skip back and forth. Now, what I'm trying to do is kind of switch to a single dam lecture. That's why we built a dam on Wednesday. Y'all remember this when we built the dam? Did we talk on Wednesday about how we're up to 11 on the Colorado River? And this has had tremendous impacts on our relationship with Mexico and on their freshwater supply to the Sea of Cortez. You may have also seen this because you're the only period that got to finish the movie where the very end was about the Mexican Colorado River Delta native fisheries. Good with all this? So before we can talk about the impact of dams, we got to talk about rivers. And how many of you have like personal experiences with a river that are like extended and you feel like you really know a river somewhere? Do you mind if I ask which rivers?
I mean, the Cuyahoga River and Big One.
Ooh, yeah. Amor, did you have your hand up?
Yeah. Birdie River.
Tight. This helps me. Because we live in Santa Barbara, many of us don't have a lot of experiences with rivers. A lot of people live in cities where the rivers don't really look like rivers or act like rivers. I made it most of my life not really noticing anything about rivers. And the first river that I really got to know was the Trinity River up in Northern California, where I used to farm on the banks of the Trinity River with my friends, the Newcomb family. I started paying attention to those rivers, it kind of changed things for me. And then I started spending my summers in the Sierra away from my friends, the Newcombs, and I started to really learn about the rivers up there in the Sierra. And I feel like, I don't know, it's weird, like you really do get to know rivers. Some of you, this is all going to be really foreign and strange. And for some of you, this is totally obvious and banal. But rivers, first of all, if you could please look up at the screen, have natural seasons. They have a dry part and a wet part. In some rivers, there's a delay because the water is stored as snow uphill. So like the Santa Ynez River, the wet part is the rainy season. But on the San Joaquin River, the rainy season makes snow in the mountains, and so the wet part is delayed by a few months until that snow melts. Obvious, right? The elevation of a river affects that delay issue. Yeah? Because sometimes the rainy season is stored as snow uphill. But you'll have like still heavy waters when everything is coming from above you. And you'll have like big thrashing, hammering, carrying all the stuff season. When the water moves super, super fast and has heavy, heavy flows. And I don't know if you've thought about it before. It's obvious once you think about it, but someone told me this during a tour of a dam, and I was like, yeah, I guess that's true. The whole point of a dam is to do the exact opposite of what a river does. The entire job of a dam is just to flip those seasons upside down. You know, dams produce electricity and irrigation water, and you don't need irrigation water when it's already raining. You all realize that you don't have to water a lot during the wet season? And so the part of the year when the river is usually flooding, that's when we want to store water, and so we stop the river from doing its flood thing. And then in the dry part, when the rivers usually don't have any water, that's when we open up the dams and let the water flow for irrigation purposes, and then we divert it. So please look up. A dammed river will do everything backwards. A dammed river will have its heaviest flows right when my previous slide said we had the least flow. And a dammed river will block and control water movement right when the previous slide says you had like heavy flows of flood water. So we used to hope in the 30s, 40s, 50s, and 60s in the United States, we used to hope that we could just interrupt that water and everything would be okay. And now we realize putting a dam in a river changes everything. It's just like, oh, backward, backward, backward. And you're going to see in a minute, I got a whole list of things that are different now. So we'll get to that list. But I'll give you a preview. You can all see the river downhill of, I think that's Hoover. But I forget. Yeah, I'm pretty sure that's Hoover Dam. That river should not look like that at all. Everything about that is wrong. That river, at that moment, should be shallow, muddy, and warm. Instead, it's deep, clear, and cold. That's all backwards. There should be riparian habitat, like sandy banks with willows and plants and songbirds, and instead it's just water to the canyon walls. Don't copy all of this. We're gonna come back to this. So don't copy this, because I got a better slide. You're just gonna waste your time, and then you're gonna get tired. You're not gonna need it, because I got this better. So don't copy all this. But there's changes in the sediment. There's also changes in the temperature, the clarity, the volume, the timing. There's changes in the salinity. There's changes in the rhythm, and there's changes in the wildlife movement. All backwards. So I'm trying to reorganize my lectures a little bit. I think that this slideshow will contain a lot of useful stuff. I want to show you where we're going first. We're going to talk about physical, ecological, and human changes. And we're going to divide those between uphill and downhill. So above the reservoir and below, above the dam and below the dam for each of those topics. So first, just how the river changes. These are the physical changes to the river, how the river itself changes. Obviously, your canyon is flooded. Water's going to evaporate. And sediment's going to slow down. I want to say something about all those, but write them down first. office, copy room, and fax to this number from the counselor's office. You'll have to ask someone to help you with the fax machine. Yeah. Flooding the canyon's obvious, right? Like when you stop it, the canyon fills up with water. So we're going to come back to that, but physically I want you to imagine that what used to be like a little trickle of water at the bottom is now just a big lake at the top. Okay. Number two, the thing about evaporating the water, please look up at me. These are your canyon walls. Okay, so we've got one canyon wall, the other canyon wall. Imagine the water's flowing kind of where my neck is. Okay, so here's our canyon, and the water's all the way down there. It's in the shade most of the day, unless the sun is right overhead. The water's in the shade. And most of the time, wind is blowing up there, not down here where the water is. Agreed? When I flood the canyon, now imagine, the water's up there by my fingertips. Now that I've flooded the canyon, the water's all the way up at my fingertips. Well, whenever the wind blows, water's going to flow across the air's going to flow across the top of the water and evaporate a bunch of that water. Also, whenever the sun is out, sun's going to hit that water. So the surface gets evaporated. And here's a crazy thought. Do you all understand that if you evaporate half the water, the remaining water has double the salt concentration? Does that make sense to everybody? Please look over here. Pretty much all the land is on its way to the sea. Everything on land will end up in the ocean someday. You know, tectonic activity, continental uplift, weathering, erosion, gravity. That's where all the salt comes from, is wearing away the rocks. Think about how many rocks are being weathered into the Colorado River. So there's always a little bit of salt being added. As rocks are weathered, you're making water saltier. Usually that makes it all the way to the ocean. That's why the ocean's full of salt water. That's why ocean salinity is always increasing very slowly. Because, you know, new water comes in, evaporation. But when you're evaporating water, the flip side problem is when we get to the downhill slide, that's going to increase salinity as we go. That makes sense, right? Another problem with dams is because you're slowing down the water, sediment is trapped. You know, fast-moving waters carries big stuff. You've heard me say this before, right? Principle of hydrology that we often forget that you really have to remember from this class because it comes up all the time. Fast-moving water can carry away buses and schoolhouses and boulders in your mom. But slowing down that water means the biggest of those things will start to settle down. What happens when that water comes to be perfectly stopped? All suspended solids will settle down. So crazy thought, all the reservoirs on Earth will eventually just be like perfect flat sandy meadows. Because by slowing down the water, that's how you get meadows in the Sierra. A beaver dam or some rock fall will plug a river, and eventually it fills up with sand, and then you get a meadow. So downhill, you can probably imagine all these problems because of what we said uphill. Downhill, number one, you've got a bunch of salt in the water, it's salinated. Number two, it's more clear. And why is it more cold?
Because they're emptying the bottom.
They're emptying the bottom, and what's that got to do with love?
Doesn't touch the sun. Or
Doesn't get warmed by the sun, yeah. How many of you have been in a plain old pool and you go to the bottom and you can feel that it's colder? How many of you free dive or have spent time in the ocean and or maybe scuba dive and you can tell that when you go deeper it gets way colder? Reservoirs are hundreds of feet deep in many cases. All it takes is usually 10 or 12 feet to make a significant thermocline. After 30 feet, you usually get a second one. After 50, 60, or 70 feet, depending on the density of the water, you get another thermocline. When some of these reservoirs are like 160 feet deep, the water that spills from the bottom of that reservoir, that's really cold. Anybody ever been to Lake Powell? Houseboats and party stuff in the desert? Spring break? The water on the surface of Lake Powell is like totally warm desert summer water. Like when you go there for spring, the surface water will be like really pleasant, like it's too hot on the houseboat, so you jump in and get it cool off and get a good little swim, and it's not cold like our ocean. 70s, really nice water. Yeah?
I forgot, why is there more salinization?
Because you evaporate all the water out, so you're leaving all the salt in it. When you get to the bottom of Lake Powell, temperatures drop like the 40s for that water. The water comes out really cold from these reservoirs. Of course, it's clear because, you know, you've kept all the sediment. And all that sediment used to do stuff downhill. Now it's all living uphill. It's not making it down. So we're going to see what that does ecologically next. Are there any questions about the physical stuff? So about those ecological changes, there's really just one uphill. When I say fragmentation of habitat, that's the only thing that you really notice up the canyon. When I say fragmentation of habitat, everybody thinks about the salmon. And yeah, it's real. Salmon is the one big, yeah, salmon. That's a big change. But it's not just the salmon, you know, a lot of terrestrial life moves along those rivers too. And the rivers that don't have salmon, they have other fish that are affected also. Crazy stuff happens downriver. You're going to need a copy for a while, and then I'll come back and talk about these. Yeah.
The book said that the uphill also, like when the reservoir fills up, it like destroys a whole bunch of like habitat along the edges. Is that?
Yeah, and we can talk about that also.
Okay.
First of all, the fish not hiding thing, you all understand evolution. Waters usually carry sediment, so water's usually kind of turbid, like at least a little bit silty for much or most of the day, much or most of the year. When the water's totally clear, those fish don't have the right behavior, they don't have the right color. A lot of them don't even have eyes on top of their head because they're not worried about getting eaten from above. Think about it, in a muddy river, a brown, lazy fish that stays low is safe. Can you imagine a brown, lazy fish in a clear blue river? The birds just see it moving slowly and wait for it to reach a shallow part and nail it. Easy osprey food. Look at number 2. When you lose that mud bottom, it's like losing topsoil in a forest. That's where all the decomposers are, where all the insects and their eggs and the nutrient cycling and stuff. Losing mud bottom in a river is kind of like losing topsoil in a forest. Number 3, we talked about the cold, right? Bottom, water from the bottom, too cold. Again, evolution, you know, if you're evolved for warm water and the water comes out cold, different temperatures. Number 4, the loss of the riparian habitat. This is one of the reasons that I ask about these rivers. Please look at me. Mountains, foothills, flatland. As rivers change their angle, the water falls at a different speed because, you know, gravity and collisions with matter. So in the steep part, rivers go really, really, really fast. Think about a waterfall. That's the fastest it can go. So where the water's moving really, really fast, it's going to tumble everything. It's going to scrape up rocks. It's going to carry away boulders. It's going to definitely tumble little rocks and gravel. It's just going to get flooded out, and all the debris and stuff, it's all getting swept away. So where the rivers are really steep, they're just big rock. Bedrock sometimes. Then, you know, where the river starts to change speed, you kind of get some, like, rapids and, like, you know, boulders will definitely settle, and, you know, football-sized rocks will settle. You'll have like some slow banks with some sediment and sand and gravel. Then look at me, when you get to the lowlands, the river's barely moving. It'll drop a few feet over like a mile. That river's practically still. So all that crap that came from uphill is now going to start to settle, and you get like a deposition of riparian habitat there, where there's like sediment and sandbars and willows that grow there. You'll get cool, like, brushy plants that always have their roots near water, so they flower at weird times. So you get all these birds that depend on that. How many of you remember my elk slide from Yellowstone when we talked about the wolf effect and unit number 2 or 3 or something? That happens where the water is slow. But what if that slow water doesn't have any more sediment? Look up here. Remember I told you that water shouldn't look like that? All the sediment is up here. Behind the dam, at the bottom of the reservoir. So that water will still slow down, but it doesn't have anything left to drop. So you lose that riparian habitat. Y'all remember that word, right? The stuff along the river. You lose that habitat value because there's no more sediment supply to keep that happening. Of course, number 5, that's another adaptation issue. If you're evolved for low salinity and the salinity keeps spiking, especially for stuff that breathes through its skin, like amphibians and fish and some plants, that's really bad. So what about the humans? Everything else was delivered? Thank you. That's actually this off. The loss of land in the United States might not be such a big deal. How many of you have heard of eminent domain? Eminent domain is the idea that if the United States needs your land for a federal project, or if California needs your land for a state project, or if Santa Barbara needs your land for a city project, they'll buy it from you. And you know, if push comes to shove, they can just take it from you, but they have to give you what's called fair market price. So if you're like, dude, I really love this land. I grew up here. I had my babies here. My grandpa's buried in the backyard. They're like, well, that sucks. Your emotional problems. But at least we're going to give you 1.2 million, because right now this would sell for 1.2 million. Fair market value. You don't get a choice about selling it, but at least you get paid. That's pretty touchy. But globally, you know, in a lot of places where they build a dam, you're just chilling at home one day and the river keeps rising. Like the loss of land for many people along rivers today has personal consequences or cultural consequences or historic. But globally, that can be really heavy. Look at number 2. I forget the exact number. I'm afraid to shoot from the hip because I might be off by a lot, but you can Google this. I'm going to try to just not get too carried away, but I believe there was 1,600 major archaeological sites in what is now Lake Powell. And if I'm wrong, I'm trying to underestimate. You all realize, right, that when we think about Native Americans of the American Southwest, the majority of their time was not spent out in the open desert, because that's really crappy. You go out there today, and you're just looking at the middle of the open desert. It's like 140 degrees all day. Like, man, this is not like a very nice environment. I would not want to live out here. Nobody ever did. There's a whole bunch of really important archaeological information, equally important culturally, along the canyons, though. Because that's shadier, it's cooler, there's places to grow your food. And, of course, there's the water and the stuff that you can hunt to eat, because everything else goes to the water, too. So look at number 2. There's a really, really sad Americana thing about number 2. The United States was for about 60 years the world leader in underwater archaeology. Because we had to be, because our feds flooded a whole bunch of really important cultural sites. Apparently during the 1930s and 40s and later on into the 50s and 60s, people would be working on a specific period in earlier American history. They've got a whole bunch of sites, and as the water starts rising, they're like, well, I gotta finish recording all this information before it's lost forever. So people got scuba certified to continue their research underwater. There was a long stretch there where people would find like a really neat ship down in like a lake in Greece or something. And they'd be like, well, what are we going to do? I don't know, call the Americans. All of their archaeologists are scuba certified. I just find it to be so wacky. And number 3 matters to you. Dams don't really last very long. The average life expectancy of an American dam is about 100 to 150 years. Do some math really quick. They were built in the 1930s to the 1960s. 100 to 150 year life expectancy. So they're going to start to go bad right around my retirement. Tight. Not a big problem for me. Just gotta try not to get fired for 19 and a half more years, and I'm out. Ghost. I got 19 years, a month, and 2 weeks, and then I'm taking like 4.5 months of sick days, and then I'm gone. Oh yeah, but back to you all. Where are you gonna be? 30s, 40s, 50s, and 60s of this century. You're going to be like raising a family, trying to start companies. You're going to get like a mortgage and try to keep the house payments under control and Keep buying cars and braces and college educations for your ugly kids. Now you can copy this all you want, but if you don't understand number one, I want you to wait for me. Because you might want to write that in different words. If you don't understand number one, I want you to wait. I'm going to leave that thing up there until the end of the period. So let me just try to explain something really quick before you start copying. How many of you have heard that Venice, Italy is sinking rapidly? Maybe you've heard that New Orleans, Louisiana is sinking rapidly. Maybe you've experienced something. You go to the beach, you put your feet in the water, and you chill and try to get sunburn on your stomach while talking to one of your homies for 15 or 20 minutes. And if the water's splashing up and over your feet and going back out and coming in and going out where you're standing, if you're in like ankle deep to exposed sand, right in the tidal influence, what happens to your body in that sand? It starts to sink. I have to hope that everyone's experienced that, right? Why didn't that sand sink without you? Like, why doesn't everything else sink? Because you have some mass that's like squeezing stuff and you're kind of displacing some of the lighter. Okay. This illustrates a principle that everybody needs to visualize. I'm going to leave that up there, but I'd like everyone to look here. Right here, on the wall. Can you see all that? Some of you might be blocked. Yeah, it's too bad for two of you. Okay. Watch this. You've got land. You've got groundwater being fed by gravity down to sea level. Where that water is moving out to sea, it carries sediment with it. The water that's moving through the ground is still moving, so because it's still moving, it still carries the teeniest little bits of stuff. Especially when you add a city on top, like you standing at the beach, you even get like a little extra heavy density on top of that kind of starts to push out some of that sediment flow through the groundwater flush out to the ocean. There's this natural cycle where water going out to the sea carries with it little tiny itty bitty tidbits of the finest particulates. Little bits of sediment like this go out to the ocean. Now, before we had a city there, and before we came along to change what happens in a river, there would also be periodic floods across the surface that would rejuvenate that sediment. You know, you lose a little bit to the ocean, but the baby Jesus brings some back down from the river. Now look at number one. When you trap all of your sediment behind the dam, you're filling up the reservoir with sediment. That's one problem in and of itself. But on the downhill side, the loss of sediment accelerates the sinking of coastal areas.
Take the yeast. Why do you put this in the fridge?
Now, here comes a really deeply compressed, extremely accelerated history of the world lesson. much all primitive agriculture had one thing in common. I want to come back to that. Raise your hand if you've heard of the Fertile Crescent. Mesopotamia, the wedge of land in between the Tigris and Euphrates rivers, that's right. Why was that crescent so fertile? This is what all primitive agriculture shared. There's one thing that your answer will tell us. Why was the Fertile Crescent so especially fertile? Is good luck?
Seasonal flooding.
Seasonal flooding. That's what all primitive agriculture shares. Modern agriculture uses tricks and plumbing and physics and engineering and stuff to move that water. But all primitive agriculture is defined by seasonal variations in water, the seasonal flooding. That seasonal flooding would, of course, provide the water, but it also provided the rejuvenating sediment. Remember that I said everything on land is on its way to the sea? A farm is a place where you can put seeds in the ground, and they'll get wet on their own, and that soil is really rich, because that's all the stuff from above you right before it goes right below you to the ocean. That's what a farm is. So look at number 2. When you block all that sediment, you've lost the rejuvenating impact of that sediment to farms. And yes, I'm talking about primitive agriculture, but that's still a thing in modern agriculture. That's still a really nice way to improve soil quality. There's occasional seasonal flooding. Number 3, of course, when you mess with the rivers, you're going to mess up your fisheries downhill. And number 4, you might have some international issues. Like, you might find this hard to believe in today's political climate, but it's kind of nice to be cool with your neighbors sometimes. The United States and Mexico had a pretty uncomfortable legal battle over water across the border. You may know that Egypt practically had a war over water across the border. Tool shed down below, please. Oh, got it? You got it?
Yeah.
So, man, why are we even building dams anymore? Oh, yeah, we're not. The United States pretty much stopped building big dams in the 1970s. We got over it a long time ago. We started to see all these problems coming up. We're like, nah. United States, for the big dams, we stopped in the 70s. For the smaller little project dams, we stopped in the 80s or the 90s. Nowadays, it's pretty rare to build even like a little micro dam. Dams are just very, very rarely used. They don't make any sense. All the water evaporates, plus a lot of it soaks in underground. Plus like the water movement stuff, you just mess up everything downhill. You know, land's gotten more expensive, and so in this country, you know, using up the land is kind of a touchier subject. So we're kind of, we don't really do the damn. Anybody that side anymore? We don't really do the damn thing anymore. You know who does though? All those countries that are trying to rev up the speed. People all over the world are like, hey, how did you all do that? And we're like fast, cheap, and out of control. And everybody's like, nice, we can do that too. So you probably, number 23, you probably want to know that the dam building era is effectively over around here, but dam building is going gangbusters in the developing world. Countries trying to jumpstart an economy, Throw in a couple of dams. Get cheap electricity, control the water supply to all your farmers, and crank up the food production. Bingo, bingo. And man, China they went big. They went really big. They started the biggest thing ever, and then they finished it. It's the biggest dam. The biggest thing ever built. It's the most concrete. It's the most labor. It's the most dollars. It's the most electricity potential. It's the largest single power plant on the planet. The biggest body ever made by humans on the planet. It's the most water held. It's the biggest perimeter of a reservoir. It's where 3 rivers meet. That's why it's called the Three Gorges Dam. Like an Adidas logo. So like it's kind of like swollen at the surface where 3 rivers come together, and there's a single dam to block that spot where all 3 of them are. Kind of visualize like a fork, I guess. Adidas logo. And man, they held this support like internationally. All these people were like, oh, we want to invest in China. China's rad. Let's all make sure that China keeps doing what China does, because the China economy just looks like a no-brainer, easy moneymaker. So everybody started throwing all their money at China. China's like, yeah, we got this, we got this, we got this. And then along the way, all these people internationally were like, you know, that's kind of a bad idea, actually. So everybody started to pull out their support. China's like, well, we're already in, we're going for it. And so it was like one of the biggest debt-built projects on Earth. It might have been the biggest debt-built project on Earth. And China assumed all this like internal debt in order to build this reservoir. China flooded, let me see if I can get this right, 2 million people's homes. Let me see if I can find another relevant number here. 1,200 villages, 2 major towns were all abandoned and rebuilt up on the edges. There was a period there where in some villages, the government would show up and go, okay, everybody, wheelbarrows. And everybody would be like, thanks, but what are we all going to do with wheelbarrows? And they're like, well, you got 2 years, and you should probably move your house up there somewhere. And everybody's like, come up? And they're like, yeah, we're about to just, and they're like, wait, but my dad's buried over there. They're like, don't worry about it. So they're like all these dead bodies that float up inside the 3 gorges. The dam has these 2 piers that have conveyor belts on them. They're called tongues, that pick up floating debris. You know, as the reservoir keeps floating up, there's like more and more mudslides, because what used to be a pretty stable rocky cliffside is becoming a muddy cliffside, and it saturates, starts to slide. And as that starts to happen, like dumps are getting included into the river, and like train depots and all kinds of stuff is just getting like folded into the reservoir as the water rises, all the edges get all smushy. So there's these 2 piers that just do this all day on the top of the dam. And they like slurp up floating debris off the top of the reservoir, and then they push it out to the sides where they have 2 separate landfills, one on each side. Pretty controversial. There's a lot of gossip about like whether China's been honest about what happened to all the people that used to live there and how they were compensated for the loss of their homes, if they were compensated for the loss of their homes. And of course, information flow in China gets a little complicated. You've probably heard that. May I use your bottle? May I use your desk?
Yeah.
Can you use your desk? Can you move that? Thanks. Watch this. Tectonic plate. 3 Gorges Reservoir. Right? There's this thing that tectonic plates do. It's called moving. There's this thing that giant reservoirs do. It's called heavy. So you've got a moving tectonic plate, and you put a heavy thing on it, and the tectonic plate will get pinned down, and you can't stop the rest of the plate from moving, so it starts to buckle. So one of the reasons that the World Bank pulled their support is a bunch of geologists were like, aren't you just going to pin down a tectonic plate and make a whole bunch of earthquakes right uphill of like the most crowded population in the world? On the floodiest river, the Yangtze? which also happens to be the dirtiest river, probably. And China's like, no, we got this. And everybody else is like, yeah, but you know the tectonic plates and the crinkling on the side of the earthquake. Who knows? I wouldn't be too excited to live downhill this reservoir myself, personally, just because I'm kind of sketched out about what's going to happen with seismology around there. While China's trying to figure out where to put more dams, the United States is trying to figure out how to get rid of them. You all know what the biggest problem is? Sediment. Does anybody know the Matilaha River, Matilaha Dam? It's like Ventura backcountry, kind of, yeah, you know, it's on the way to Ojai from Ventura. It's a pretty small dam, doesn't really do anything for water flow anymore. It's mostly full of sediment now. So we get these occasional storms that move a lot of sediment, you're all aware of that. And the Matilaha Dam was pretty small, and then like in a couple of big storms, it just went like whoop, 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 and it took like 3 or 4 big storms, it just got full of sediment. So mostly, water is just kind of like cruising across the top of the reservoir, which is otherwise just a big sandy meadow. And the water like will cascade over the top of the Matilaha Dam in 2 different places. So Ventura, I think it's Ventura County. I don't know either. I think it's Ventura County. They're like, no, we don't want it anymore. And the feds are like, yo, we could reintroduce steelhead if we could just get rid of this one dam. And so Ventura's like, yeah, we'll put in some money, we'll get rid of the dam, we'll do the steelhead thing. And the feds are like, yeah, we'll get rid of it, then we'll do it. And this plant was picking up all the steam, and people were like, oh, we can breed the steelhead. Everybody's like, yay, schools can breed steelhead. And people were like, okay, we'll use all the concrete to like landfill when we build like new roads. We'll use it for road bed to expand Highway 33. And everybody's like, yay, we'll use all the concrete for road bed. And people were like, what are we gonna do with all the sediment? And everybody's like, nobody thinks that we can't figure out what to do with all the sediment. We couldn't come up with enough money to buy enough land to spread out all the sediment that's in the Matilaha Dam. The removal of the dam is so easy. When I tell my students that there's no way to get rid of the dams, kids are like, well, dynamite. Like, I know, it's not a challenge to ruin the dam. It's actually pretty easy. You can just sit back and wait, and they'll just break. It's not a challenge to demo the dam. What the turkey you're going to do with all that sediment? Water flows on its own, it sinks into the ground. If you let it out slowly, you can deal with the water. But the sediment is just a lot of sediment. Let me give you a couple of numbers. I don't want to get to the next study goal, I just want to talk about this dam removal stuff. Glen and Hoover dams, on average, receive 2 dump trucks of sediment per second. That means in the history of these reservoirs, they've been filling up by 2 dump trucks per second. Right? So they're about halfway full now with sediment. How do you get that all out of there? Can you imagine the production line to just keep up with the sediment flow? If you were taking 2 dump trucks out per second, right? Imagine what that would just physically look like. Like, vroom, vroom. I have to go faster than that because that was not a second separating those. 1 1,000, 2 1,000, 3 1,000, 4 1,000, 5 1,000, 6 1,000, 7 1,000, 8 1,000. Where would all these dump trucks go? Can you imagine that freeway? Like you've seen what happens with the dump trucks and the sediment, right? Like where are you going to put all this stuff? We filled up like a small residential area. And we're going to deal with sediment for God knows how many years. Imagine a reservoir, 2 dump trucks per second for 80 odd years now. Yeah.
Why don't we just like dump it into the ocean like the little ones? Because it's supposed to go in there anyways.
Oh, I know. It's just like, how do you get rid of it? Because there's all, like, natural water flow already has natural sediment flow. That's already a hassle to deal with. You've got all this bonus built up. You know, like, imagine, like, I don't know, trash flow at your house. Like, trash is already a pain in the butt to deal with. What if you just, like, open the room one day and you're like, oh, crap, this whole room is just solid trash, and I gotta get rid of it in my little... You know, residence time would be like my little brown container that I take out every Tuesday morning. Like, I'm still making trash on my own, and then I gotta get rid of all this extra trash, and you can just barely, like, trickle. It's like, oh, we can top off a little bit more. So we can use our rivers to manage a little extra sediment flow, but they're already kind of burdened by sediment flow as it is. You've seen that heavy sediment flows are hard to manage. Imagine the volume you're talking about, 2 dump trucks per second in the Colorado for the big dams. You know, there's a lot of sand in the desert, y'all. You want to know where I think this is going to end up? Oh! I got a couple other problems. I forgot to tell you the other problems. How much time do I have? Oh, yeah, I got this. Hey, check out these problems. You ready for some interesting problems? Here's problem number 1. I won't take it with you, I swear. Look, this is the canyon, okay? If I want to build a dam right here, I just dump concrete over the edges because gravity, right? If I want to get rid of that concrete now, you all realize I got to lift it out and drive it away. Right? Here's another problem. 1930s, 40s, and 50s, you know what was cheap? Everything. Material, energy, labor. Nowadays, materials, energy, and labor are more expensive. We've got all these, like, labor laws and pesky environmental regulations. Everybody's got rights now. So we can't afford to get rid of them. We got no place to put all that stuff. So here's my guess. I've got this figured out. When I'm in my retirement, you can come find me on the beach in Mexico, and we'll see if I was right. I think we're going to make new rivers to go around the reservoirs. I got it. Figured it out. We're just going to take the big reservoir, and we're just going to divert the river around it, and just leave that as like a big sandy meadow held up. No more water coming in, hopefully. My plan. Because honestly, for the big dams, we don't have any other plan. Little ones are so hard to get rid of. Okay, bye-bye.